What happens if you have things like an oxygen or a nitrogen in the ring? And you see that in aromatic compounds. How is it that they are participating in this? Well, let's look at sulfur and oxygen. They're in the same column in the periodic table. Let's look at those first. Sulfur and oxygen have 6 electrons. As a result, they have 2 single bonds and 2 non-bonding pairs in every Lewis dot structure. In an aromatic ring, the 2 single bonds are used to form the ring, so that that's to help it close the ring. One of the non-bonding pairs is going to be in the pi system, and it'll be perpendicular to the ring and be able to participate with the other p orbitals in that ring in order to make the aromatic pi system. One pair is in an sp2 orbital that is in the plane of the ring. Now, if you look at the system that will be aromatic for that, the oxygen having 2 electrons in the non-bonding pair in that pi system means there's only 4 other electrons in the ring. So that gives a 5-membered ring 4 carbons and 1 oxygen to make it aromatic. And that's why something like furan is aromatic, because it has 2 double bonds, 4 electrons, and an oxygen with a non-bonding pair, 6 electrons. That's aromatic. Nitrogen can do a similar thing, but it's slightly different because it has a different number of electrons. What you will have is that a nitrogen can do one of 2 things. It can either have 3 sp2 orbitals that form 3 single bonds. 2 of them are going to be to carbons to form the ring, and 1 will be to a hydrogen outside of the ring. Then you will have a leftover p orbital that holds 2 electrons, basically what would be the non-bonding pair, participating in the pi system. So this gives you a 5-membered ring with 2 carbon-carbon double bonds and a nitrogen there with 2 electrons in the pi system and a hydrogen on the nitrogen. There's another thing that a nitrogen can do, and that is it can have a double bond to it. So what happens is 2 sp2 orbitals form the single bonds, and there is a p with 1 electron that is in the pi system. This gives you a non-bonding pair that is actually in an sp2 orbital that's in the plane. So that p orbital has 1 electron, just like a carbon would have. And there's 5 other carbons in that ring, each one giving 1 electron. So you've got 5 carbons giving 5 electrons and 1 nitrogen giving 1 electron, and it's aromatic. Where you see that is in pyridine, and where you see the other one with the 3 sp3 orbitals forming 3 single bonds is in pyrrolidine, and we'll look at those in just a little bit. The easy way to see what is going on is if the atom does not have a double bond to it, and the remainder of the ring is conjugated pi system, then the non-bonding pair must be in the pi system. If the atom does have a double bond, then what's happening is that atom is only providing one electron through a p orbital, and the non-bonding pair is in an sp2 orbital that's in the plane of the ring. Therefore, each atom that has a double bond on it provides one electron. Every non-bonding pair, that would be an atom that has no double bond to it, it has a non-bonding pair that's in the pi system providing 2 electrons for all these aromatic systems. And we're going to look at several of these with the drawing so you can see this. I'll go over this all over again because I know right now your brain has just exploded. Here's an example. How is furan aromatic? Remember I said oxygen has to have 2 single bonds and 2 non-bonding pairs. And you can see that right there. How is it being aromatic? Well, count the number of pi electrons. The first thing we have to do is find the 4 carbons. 1, 2, 3, 4. Each one provide 1 electron. Anything that's in a double bond is providing 1 electron. So 1, 2, 3, 4. Then the oxygen has no double bond, so it must be providing a non-bonding pair. 5, 6. Oop, it's aromatic. 6 electrons in total gives an aromatic ring, and it's planar. Is this compound aromatic? If it is, explain by counting the electrons. Explain what is a hybridization of each atom, and in what type orbital is each of the non-bonding pairs. Well, if I go over here, I can see this atom, this one, and this one all are in a double bond. So each one of those is providing 1 electron. That's 4. This one isn't in a double bond, so it must be providing a non-bonding pair. So 2 electrons. 1, 2, 3, 4, 5, 6. It's aromatic. If I look at this nitrogen, because it has a double bond on it, its non-bonding pair is in an sp2 orbital out here in the plane of the ring. This nitrogen, because it doesn't have a double bond to it, its non-bonding pair is in the pi system of the ring, but the nitrogen must be sp2 hybridized. It's just the non-bonding pair is in the pi system of the ring, and what we're going to see later on is anytime you have a non-bonding pair in the pi system of the ring, it is not basic anymore. It cannot react with anything. It can't accept a proton. It can't be nucleophilic. It's tied up in that pi system. However, this one, it has that non-bonding pair stuck out in an sp2 orbital, really kind of naked out there, stuck away from the ring, and it is basic. It can be protonated. It's available for a nucleophilic reaction, although it would probably come undone because you would have to have a positive charge on that nitrogen, so it would back out with time. So 4 electrons, 1 from each atom in the double bond, and the nitrogen that is on the top is in a double bond, so the non-bonding pair is in an sp2 orbital. The nitrogen in the bottom has no double bond, so the non-bonding pair is in the pi system. That's 2 more electrons. Altogether, you had 6 electrons. Okay, ions can be aromatic too. If I look up here at cyclopentadiene in the very top, this is non-aromatic. Why? Because this carbon interrupts the conjugation of the double bonds with each other. There is no p orbital here, making the ring complete with the pi's. However, if I remove a proton, If I remove a proton from that methylene where it's pointing, that's going to leave a negative charge there. That negative charge is 2 electrons in an orbital. If you look at this system now, it can be conjugated. And what we find is these 2 electrons end up being in a p orbital perpendicular to the ring. So then there is p orbital, p orbital, p orbital, p orbital, p orbital. This ring now is completely conjugated. But even though we only have a 5-membered ring, look at how many electrons we have. 1, 2, 3, 4, 5, 6. This is aromatic now. And the ion itself is aromatic and has great stability for an anion. Normally, anions are not that stable, but that particular anion has a good amount of stability. The cyclopentadienyl anion is a 4n plus 2 electron system. It's aromatic. It's much more stable than a normal secondary anion. Look how acidic it is. It has a pKa of 16. That's about the same as water. That's amazing that a carbon would have a hydrogen that can lose a proton as easily as water can. What does that due to? The great stability of that aromatic cyclopentadienyl anion. The cyclopentadienyl cation only has 4 electrons in the system. Let's count them. 1, 2, 3, 4. And there's p orbitals all around, so it is conjugated, but there's no electrons from the p orbital here because of the positive charge. Those 4 electrons are anti-aromatic because 4n is anti-aromatic. So if this is planar, it's going to be very unstable. And what we find is that this is very difficult to form. Normally, forming a carbocation next to a double bond is a relatively easy thing to do. But when we do it in this circumstance, where it forms an anti-aromatic carbocation, it's very unstable, so it's more difficult than forming a primary carbocation. So which of these are aromatic and which of these are anti-aromatic? If I look at these systems, you will see that this one has 1, 2, 3, 4, none there, 5, 6. 6 electrons in this, that's aromatic. What about this one? Count them and figure it out. 1, 2, how many here? Well, you might have thought to yourself, this is not conjugated, so it's not aromatic or anti-aromatic. But it is because there's a non-bonding pair on the oxygen that can participate. So no electrons here. 1, 2, 3, 4, 5, 6. That's aromatic. Let's look at this one now. 1, 2, 3, 4, 5, 6, 7, 8. That's 4n, 4 times 2. This is anti-aromatic. What would happen with this anti-aromatic compound, if you were able to form it, it would be so unstable, planar, that it would try to pucker to relieve some of the conjugation, some of the overlap, so that it would not be anti-aromatic. Aromatic compounds can be fused rings like naphthalene and anthracene. And if you count these up, you're going to actually find 4n plus 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is 4 times 2 plus 2. And this one is going to be 14 electrons. However, 4n plus 2 doesn't always apply to fused rings. There are some fused rings in which that are aromatic that don't have the 4n plus 2, so don't let it mess you up. If you see what looks like a bunch of benzene rings fused together, it's going to be aromatic. So how many pi electrons does this compound have? Well, the key to doing this is to remember that a positive charge means it's an empty p orbital, and so you count no electrons there. So the remaining electrons are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 electrons in the pi system, and it is an aromatic compound. What is the hybridization of the nitrogen in N-methylpyrrole? Prior to looking at aromaticity, you would have looked and said non-bonding pair and 3 bonds. That means sp3 hybridization. But this is not sp3 hybridized. In order to complete that ring and give it 6 electrons for an aromatic compound, you will find that the nitrogen is sp2 hybridized. How many electrons are in this pi system? Again, the positive charge means a p orbital that's empty. So you have 4 carbons in double bonds. That gives you 4 electrons. This compound is anti-aromatic. This carbocation is anti-aromatic. How would you classify this compound? Well, let's count the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is 4n, so this is an anti-aromatic compound. How would you classify this? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and none there. So this has 10 electrons. It is aromatic. Which of these compounds can you classify as an aromatic heterocycle? Well, a heterocycle means that you have a heteroatom in the ring. So automatically, aniline here cannot be classified as an aromatic heterocycle. It is aromatic, but it's not a heterocycle. If I look at these 3, they're all heterocycles. Okay, let's look to see if they're aromatic. Let's go and count the electrons here, and you will see you have 6, 7, 8. That's anti-aromatic. Let's look here. 1, 2, 3, 4, 5, 6, 7, 8. That's anti-aromatic. Here, though, we have 6. 1, 2, 3, 4, 5, 6. Aromatic. Remember, the nitrogens that have no double bond to them provide 2 electrons. The nitrogens that have a double bond to them are only providing 1 electron to the pi system. Which of the following compounds is not aromatic? Well, the first thing I do when I look for aromaticity is I look to see, is it conjugated? And all of these have conjugation, whether it's through double bonds or through a non-bonding pair in the pi system, except for the last one. If you look at this one, you can see there is a break between double bonds with a methylene, a carbon with 2 hydrogens on it. So that compound cannot be aromatic. Which of the following compounds is anti-aromatic? To look for an anti-aromatic compound, you have to look for a system that has 4 times n electrons. So either 4 electrons or 8 electrons or 12 electrons. So if I go through the following thing, everything is conjugated. So if I look through, I can see that this has 6, this has 10, this has 2, which is aromatic and not anti-aromatic, and this has 2, which is aromatic and not anti-aromatic. But if I look at this one, there are 4 electrons in this ring. This is anti-aromatic. How many pi electrons are in imidazole? Well, let's look. 1, 2. This provides only 1 because it's in a double bond. 3. This provides 2 because it's a non-bonding pair that's in the ring pi system. So there are 6 in this aromatic ring. Which of the following is the best way to describe the cyclopentadienyl cation? Well, cyclopentadienyl cation is a 5-membered ring with 2 double bonds plus a positive charge. So you have a p orbital that's empty. That means 4 electrons in its pi system. It's anti-aromatic.